So let's go through an example of how we would actually calculate a regression using SPSS, the output that we would get, and how we'd interpret that to make prediction. So we're going to be using an example of what is the effect of attendance on exam scores. So this is based on an actual set of data from a class that I taught many years ago. And the predictor is attendance in class. So we know this comes first temporally. So theoretically, we can argue that this is a predictor, that you attend class prior to the final exam. So basically, this was a class where I took attendance. This was an in-person, non-asynchronous, non-online class. And I calculated the attendance in the class, and it was a summer class, on their final exam score. So I know that attendance, how often they're attending my lectures, is a temporally present predictor of their outcome, exam score. And that's what I was going to look at statistically speaking. So again, this is just a reminder that whenever we're talking about predictor and outcome, it may be arbitrary, but generally the predictor is going to be whatever variable we can make the logical or theoretical argument would come first. And sometimes this is a very easy argument to make. Sometimes it's more based on theory. But also think about practically, which of the two predictors would you actually, or variables, would you actually have ahead of time to be able to do prediction? So if I'm wanting to predict attendance by exam score, I'm not going to have their exam score until the attendance is already done, which means it's not going to be useful as a predictor for future populations. In other words, someone coming into the class, I wouldn't be able to predict their exam score, their attendance by exam score, because I'd already have their attendance data. However, if before the test I wanted to ask the question, who do I think will do well, I could use attendance. Likewise, if we're doing prediction of performance in a job, I may be able to give someone a cognitive ability test before they ever become a member of the organization and have the job. So I could use that predict. But if I already have performance, there wouldn't be much of a use of predicting cognitive ability by performance. Now it depends again on the use. Likewise, if I already have your college GPA, it really doesn't matter if it relates necessarily to a score you had on a test. But if I gave you that test, the ACT, before you ever went to college, then I can predict the outcome, and the outcome being performance in college, that GPA again. So my example data here, so this is from SPSS. I have attendance, I have total points on the exam, and I have some additional variables here, but honestly, I'm only going to be looking at these two, attendance by total points. So we have the attendance record, and we have the total points earned on the exam. So in SPSS, I'm going to go to Analyze, Regression, Linear. So this is where I'm going. So I notice that under regression, there is curve estimation, binary logistics, multinomial logistics, ordinal, probit, nonlinear, weighted estimation, two-stage least squares, optimal scaling. There's a lot of things that we can do with regression. We are focusing simply on using regression to take one step above what we normally do when we correlate or do correlation. So we're going to select regression linear, and we do that for most simple regressions. That's going to bring me to this one, and again, I have to define who my dependent and independent variables are. And remember, independent variable in this case is our predictor, and dependent variable is our outcome. So my predictor is attendance, so I'd simply click on attendance and click the arrow in the middle of the screen to bring it over into the box under independent variables, and then I'd click my outcome, total exam points. I'd click that arrow and bring it over to the box. So my DV is my outcome, my IV is my predictor, and once I've done that, I'd click OK. And this is going to give me results. So the results section, the output from SPSS is going to look like this. We're going to have a fair amount of information in here. The model summary is more about, this is going to look the same, whether it's a correlation or a regression. However, the reason we're getting a model summary is, remember, regression is capable of doing much more than simple regression. So this is going to become more and more important. In fact, some of these scores are going to become more important, like the R-square adjusted, the standard error of the estimate, in other analyses we use with regression. But in this case, really all we're interested in is taking a look at the R and the R-squared. And honestly, the only thing we're really getting from this box for simple regression is that R-squared information. So our correlation R is here, and our R-squared is here. Now note, we're not going to report the actual R. We're going to report R squared of the effect size, assuming we have significance. Coming down to this box is where our actual degrees of freedom is. It's that second box under residual. So notice again, we have 3 degrees of freedom here listed. A degrees of freedom of 1. This tells us how many variables are in this model. Again, for our purposes, we don't need to give this information out. We're doing a simple regression. The second one is the degrees of freedom n minus 2. So again, that tells us what our actual degrees of freedom that we're going to report. So if we're reporting this, we'd be reporting parentheses 67 parentheses. That's our degrees of freedom. Then we're going to get this box. So again, thinking of the first 2 boxes really gives us more information when we're doing more complex analysis. Really, the only thing we're gathering from that box is our degrees of freedom and our effect size. Everything else is going to come from the third box we get, which is the actual regression analysis. So we're going to get 2 pieces of information. We're going to get the constant and the attendance. So again, the y-intercept is here, and y-intercept is going to be important. What that is what score would you have if you had 0 attendance? So basically, if someone never attended class, our prediction model would start, our line of best fit would start 0 attendance with a test score of 62.507. So maybe this test is a little too easy. That's the first thing that I want to get off of this, the y-intercept. The second number we get is the amount of change in the DV for every unit change in the IV. So remember that 1 unit change in the IV is 1 day of attendance. And what this is telling us is that for each day of attendance, test score is predicted to go up 3.842. So for instance, just right off the bat, we can use this data to go, what if someone only attended once versus someone that attended 0 times? The person that attended 0 times, we'd expect their predicted outcome to be a test score of 62.507. If they attended only once, we'd expect it to go up almost 4 points. We'd expect it to be approximately a test score of 66. And likewise, if they attended twice, we'd expect it to be almost a 70, basically a C. If they attended 3 times, we'd expect them to be in that C range, a little bit over 70. So basically, we're just multiplying their number of attendance, and in this case, the predictor variable, by this constant, the B weight. And notice that's B, capital B, not beta. Beta is presented elsewhere. So the actual correlation we're going to report, which by the way is the exact same number that we got with the regression or the correlation information previously, is the beta. And this lets people know that we've actually run a regression, not an actual correlation. And finally, we're going to get a statistical significance test. We're not actually going to report the t. Notice that you may be familiar with t as a statistical technique, and it is. However, in this case, it's simply a way to test whether or not our regression is significant. The reason we have a separate test for this is, again, the complexity that regression allows us to do, looking at multiple variables. But in this case, though the t is going to be different than the r, the statistical significance should be the same. So in this case, we know the statistical significance level, the p, is 0.002. Definitely below 0.05, there is a statistically significant relationship. And here's what it looks like graphically. So this is a scatter plot. And notice that basically the attendance in this case, it was a short class. This was a summer class over 1 month. So attendance ranged between 1 and 5 weeks. So people that attended all 5 weeks, this was their scores: 4 weeks, 3 weeks, 2 weeks, 1 week. So notice that the people that actually that only attended once actually did a little bit better than prediction. The people that attended twice is pretty much right on that line. And we also start to see that there are people on the line, but their error of both above and below increases as more and more people are attending. Most people attended all 5 weeks. So how would we report this? Attendance is statistically significantly related to exam score. So we open with basically what was found. Attendance, which is the predictor, or is a statistically significantly related to exam score, which is the outcome. We then report it. We first report the B weight, so that how much does it increase? In other words, for each unit increase in our outcome, or our predictor, how much do we expect to see an increase in our outcome, exam score? Its B is 0.3842. Our beta, the actual test statistic, is 0.369. Now, there's a couple of ways you can present this. You can present it as the actual test statistic, T, with the actual degrees of freedom, 67, or you could simply ignore the t and present the beta. Either way is acceptable. And then the actual test statistic, and then the p-value. So again, in plain English, on average, for every one class attended, students increase their exam score by 3.842. A quick note on decimal points. You want to be consistent in the decimal points you use. It really does vary. Generally, a good idea is at least to go to 2 decimal points. You can go to 3, you can go down to 1. But if you did report a beta, so with the B, of 3.8, then you'd report a beta of 3.6. You'd report the t-test of 3.25, rounding up. And then you always report the p, though. If it's less than 0.001, that's the only time you can actually go less than. P is never 0. Never report a P of 0.00. The worst you'd always report is less than 0.001, or the best you could report. There's always a chance we're wrong, and that's what we're representing by that P. What is the chance that we're wrong in this prediction? In this case, it's less than 1%. Hopefully that helps you get a little bit of an idea of how you'd actually report this, but let's also talk about how we'd actually conduct predictions now based on this information. So again, we're looking at those predicted scores, that constant plus attendance, those two numbers that we started with in the coefficients. So our regression equation is bx plus a. So what does that mean? That means the b weight of their score plus the y-intercept. So we take b weight, 0.3842, whatever their score is, in this case, number of attendance, 1 through 5, and then we add the y-intercept, and that gives us our y prime, our predicted score. So Nancy attended 3 classes. What would you expect her exam score to be? So we'd simply take the b weight of 3.842, times it by her number of attendances, 3, and then add it to the y-intercept, 62.507. So it's this equation. We calculate it, 11.526 plus 67.507. We'd add those together. We'd expect Nancy to score a 74.033 on her test based on her attendance. Now remember, we didn't have perfect prediction. There was error, so we not necessarily know that was Nancy's score, but that would be a better guess than just guessing what Nancy's score would be. So the main points of this is the results of regression analysis indicate how accurately the IVs can be used to predict the DV. And this is based on the R, the beta, and the R squared. So how strong is the effect? How much change in the DV occurs when there is 1 unit change in the IV is the B weight, and what score in the DV corresponds with 0 on the IV, the y-intercept or constant. This information can then be used to predict any DV score from an IV score in the future and to know how accurate that prediction is going to be. We use the regression line of best fit, to know how much change in the outcome occurs when there is a certain amount of change in the predictor. So the null hypothesis, the hypothesis that there is nothing going on, the null hypothesis in this case is there is no relationship between the predictor and the outcome. The slope of the line, the beta, is 0, so there's no relationship. Our alternative hypothesis, and this is basically the predicted hypothesis, is the predictor and the outcome are related. The slope of the line is significantly greater than 0. So again, that beta is more than 0. There is an effect there. So hopefully this kind of gives you a broad idea of what we're using regression for, how regression differs from correlation, and how we'd actually calculate a regression using SPSS, the statistical package.